The kind of independence that we're talking about in naive Bayes is not mutual independence, it's conditional independence, and there's a difference between the two. And the difference is really quite important. So suppose I have two events, two variables representing going to the beach, that's B, and getting a heat stroke, that's S. Now, going to the beach and getting a heat stroke are not independent. You are much more likely to see the two together than separately of each other, right? So the joint probability of going to the beach and getting a heat stroke is, you would expect it to be a lot higher than the probability of them just coincidentally happening by themselves. So that's the probability of going to the beach multiplied by the probability of getting a heat stroke overall. So they're not independent, they're positively correlated. So it would be wrong to assume that they're independent. But conditional independence says, wait, maybe there is an external factor, a factor that we're not considering. It's not either B or S. It's some other factor behind the scene that is affecting both the probability of going to the beach and the probability of getting a heat stroke. And in this example, so suppose this event is whether the weather is hot or not. So if you look at it this way, the events could actually be independent, because after all, it's not going to the beach that causes a heat stroke. It's the hot weather that causes a heat stroke. And the hot weather also compels you to go to a beach because it's nice, right? So just by themselves, the beach and the heat stroke are not related. You could go to a beach in Scotland any day and not get a heat stroke. But you generally don't even really want to go to a beach in Scotland unless the weather is hot, right? When the weather is hot, it's actually really nice down there, and you are compelled to go there, and you are also more likely to get a heat stroke. So it's a single factor that is affecting the probabilities of you going to the beach and you getting a heat stroke and making them quite correlated. So that's the idea of a conditional independence. The conditional independence says that behind the scenes there's this hidden factor H, whether the weather is hot or not, and if you factor that into the equation, going to the beach and getting a heat stroke are actually independent of each other, right? Because it's the hotness of the weather that determines both events. So that's conditional independence. And the idea there is, yes, there is a connection between going to the beach and getting a heat stroke, but all of that connection is explained by this hidden hot weather event. So that's conditional independence. The translation to classification is you assume that your class is that hidden parameter. So what you're assuming is that the attributes, they're not independent of each other, but any kind of a dependency between the attributes is explained by the class. So if you know that it's digit 3, you can assume that the pixels are uncorrelated, because it's digit 3, it's the 3-ness of the bitmap that puts pixels in particular positions. It's not other pixels. That's the assumption. So I hope this makes sense. It's really an important difference between conditional and mutual independence. And what you have in the naive Bayes classifier is conditional. You have this hidden factor, which in this case is just a class.